Oh, come on. Speaking of electrons and photons, that didn't work. Okay, so here we are. We're early 1900s. They had gravity figured out. They were struggling to explain that phenomenon. Charged balloons, it's attracted, sometimes it's repulsive. They really don't know what's going on. They know that they have something called the electrostatic force. So, the electrostatic force, I'll explain what that squares in just a second. That equation is F equals K Q1 Q2 over D squared. Now, in contrast to that, you have the gravitational force, which is M1 M2 over D squared. So if you take AP Physics 2, we're going to spend a lot of time talking about this equation. What it does is that it calculates what's called the Coulombic forces between charged particles. So Q1 and Q2 are just charged particles. It could be two protons, it could be a proton and electron, it could be a soap bubble in the Van de Graaff generator. Here's the point. The K is just a number. Don't worry about it for now. It has a specific value. Do not worry about it for now. It's just a number. And then you have charges, and you divide by D squared. So coulombs are a fundamental charge of nature. Over here, you have mass. Mass is a fundamental thing of nature. So you're both, in both situations, you're multiplying a fundamental value of nature, whether it's charge or mass. They both have some constant of proportionality, either the K or the universal gravitational constant. And they're both inversely proportional to D squared. So mathematically, the calculations of these forces look very similar. And so that's one of the things physicists thought for a while, is like, hey, can we find a grand unification theory? Can we combine gravity with electrostatic because of the fact that both equations are so similar? Turns out we can't, especially on a quantum level, because that gets even weirder. But here's the point. They have a similar structure. Increase the distance, the force becomes weaker. So they had an understanding of this. They really didn't understand the mechanism, like why the balloons repelled or why the balloons attracted. They could calculate it, but they struggled to figure out what the particles were. So, anybody remember what a guy by the name of J.J. Thomson did?
Nope.
All of your Chemistry 1 teachers are screaming at you right now.
Gold foil test?
Huh?
Is he the gold foil test?
No, that's Rutherford.
The atom structure?
Kinda. He was the first one to find the first subatomic particle. It was the first subatomic particle found. Chihuahuas, because they're the easiest, okay? Because chihuahuas are running around. So Thomson discovered the electron, okay? Actually, he found the charge to mass ratio on it, but he discovered the electron. Now, this created a problem. This was in late 1918, okay? The other thing that you'll remember, we're going to talk about Thomson, Rutherford, Bohr. All of the people that were doing this research were physicists. The chemistry department always talks about the history of the atom. The chemistry department had nothing to do with the discovery of the structure of the atom. They really didn't. All of these guys are physicists for two reasons. Number one, physicists were basically out of a job at that point. Okay, it was a dead-end job. They had gravity figured out. They thought, okay, really, we have nothing left to discover. We didn't know that there were other galaxies. We didn't know there were subatomic particles. We didn't know fusion. There's a whole bunch of things we didn't know. Physicists were basically out of a job. They said, okay, hey, we'll figure out the structure of the universe. That's on us. Chemists at the time were finding a better way to purify cocaine. True story. Because, no, that's a true story. Because at the time, in the early 1900s, you could buy, Coca-Cola, Coke came from the word cocaine. Coca-Cola used to have cocaine in it. You used to be able to buy cocaine over the counter. Okay? True story. You can't anymore, obviously. So that was always the running joke, was that the chemistry department was figuring out how to make better drugs, the physics department was out of job, and they were stuck trying to find the structure of the universe. So, once they found the electron, this was problematic. If they're negatively charged particles, what else does there have to be?
Positive.
Positive. Could we be here having this discussion if the only thing that existed in the universe were negatively charged particles?
No, not chance.
No, because look what happened when I tried to push those two balloons together that were negatively charged. What did they do? They repelled each other. You could not build anything if everything in the universe was negatively charged. Same thing is true if everything was positively charged. If the universe just said, we're just going to make protons, cool, we wouldn't be here having this discussion. Worse yet, Mother Nature says, we're just going to make mass, but we're not going to give any of it a charge. We're just going to make nothing but neutrons. Cool. We wouldn't be here having that discussion either. But neutrons, you can pack them very densely together because of the fact that they're neutral. Okay, neutron stars are incredibly dense, for example. So, because they found the electron, they said, okay, hey, there has to be protons. Cool. And so, the first model that they had was what's known as the plum pudding model. Ah, does that ring a bell? Okay, right? So, or cookie. So it was British, this is all done at Cambridge. So the plum pudding model, you have to look very proper and British. So, on the plum pudding model, here's the struggle. So any criteria, and this is where the squirrels come into this story. Any atomic theory had to explain the stability of atoms, okay? So here's where squirrels came into my room. So I have literally been teaching behind this desk since the fall of 1994, okay? I've spent a lot of time behind this desk, okay? I walk in every morning. One of the things I don't worry about is like my table has changed into a squirrel. Okay? It's like, what happened to my table? I don't know. But I got squirrels running around the room. This is bad. So the senior prank last year was that they took my table, moved it away, and took those two squirrels and had the squirrels sitting here in place at the table. That's how the squirrels story got started. So, however you explain the atom, it has to work over a long period of time. This table has been a table since 1994. It's going to be a table for a long time, okay? So whatever structure that you have has to explain why atoms don't change over a period of time. So the plum pudding model basically took the idea of the atom, and at the time they were viewing the atom as like a tiny little Lego block. And they said, okay, now there's negatively charged and positively charged. So they said, okay, we're going to envision this as being like the positive and negatively charges embedded within the atom. This gave the advantage of stability because it balanced repulsion and attraction. So you had the repulsion from the like charges, but you also had some attraction from the unlike charges. And they said, okay, here's a cool way to deal with this. Cool. It worked because it explained why atoms were stable. Now, along comes Ernest Rutherford. Now, you have to understand Ernest Rutherford. Ernest Rutherford was actually from New Zealand. Big guy, had a great handlebar mustache. If I could grow a handlebar mustache like him, I would. But, so, and again, it's important to remember that Rutherford was a physicist. He was not a chemist. So at the end of the day, physicists we just like to smash stuff together. So the famous story, or analogy of how physicists view things, is that if you gave a Volkswagen Bug to a physicist and said, hey, what's the car made of? I don't know. Let's find out. So you get the car up to 20 miles an hour and you run it into a wall. Oh, look, a bumper fell off. A bumper must be part of the car. Cool. Nice. Well, if 20 miles per hour is good, 200 miles per hour is going to be better.
I agree.
Get it up to 200. Boom, smash it into the wall. Okay?
Lots of particles.
Oh, there's glass. There is a door.
There's an edge.
Nice. Okay. 2,000 miles per hour is going to be even better. Bam. Oh, look, there's an engine inside. That's cool. What's the engine made of? I don't know. Let's get 2 engines get them in opposite direction at 20,000 miles per hour, and smash them together.
Yeah.
Oh, look, there's the pistons inside the engines. What are the pistons made of? I don't know. Let's smash them together at 200,000 miles per hour in a particle accelerator, which is basically what physicists do. So we smash things together, and we figure out what the world is made of. So that's how Rutherford approached this. So somebody mentioned gold foil. So the unique thing about gold is that it's very, very malleable. And this is not scientific, but it works. Gold atoms are very sticky, okay? So what that means is that you can take gold foil and work it so that it's literally almost one atom thick, okay? Like literally, gold foil was so cool, and you can do so much with it. Like very, very swanky weddings, they will have gold foil on the cake where you can actually eat it, okay? So Rutherford is a physicist, so he goes, okay, I'm going to take some gold foil. That's his target. Even though it was incredibly thin, if you held it up to the light, you could not see through it. So to us, it would appear opaque, like you couldn't see through it. So Rutherford needed something to shoot at the gold. So they knew about radioactive sources, so he used, I think it was like thorium-235. Thorium-235 would undergo radioactive decay, and it would emit these particles. He didn't know what they were. So he called them alpha particles. Did not know what the particles were. So this was inside a box, and there was an opening. So as this stuff emitted these alpha particles, only alpha particles that were going in a straight line could make it out of the box, okay? So these alpha particles are coming out. The most common misconception everybody has is that you can see the alpha particles. This is the nucleus of an atom. Let me give you some perspective on scale. We've talked about this. If this is the thickness of here's your edge of the aluminum foil, right here, okay? It would take 94,000 aluminum atoms stacked side by side to get the thickness, not this, right there, that edge, 94,000. To scale, if my hands were the size of the aluminum atom, the nucleus would be a human hair right in the middle, okay? That, and then an unimaginably small dot. That's where the St. Bernards and sheepdogs are hanging out, is that dot. The Chihuahuas are moving very, very, very quickly around and creating space. The Chihuahuas create space, the St. Bernards and the sheepdogs create mass, okay? So, what Rutherford did is that he took basically like a battery and had a positively and negatively charged plate to it, kind of like the balloon. So imagine the balloon is negatively charged and the blanket would be positively charged. And he would shoot these particles through this. And what he found is that the particles would go away from the positively charged plate and they would deflect down towards the negatively charged plate. So therefore they had to be, they would be repelled by the positive and they would go towards the negative. So the charges, this particle had a positive charge because it was repulsed by the positive and attracted towards the negative. So these particles had a positive charge. You could not see them. So it's like, well, how did he know they were there? What he would do is he would put like a phosphorescent screen. So a phosphorescent screen, every time one of these alpha particles would hit the phosphorescent screen, you would see a small flash of light because it would excite the phosphorescence. So the first thing he did is that he figured out the charge on the particles. Oh, yeah, they're positively charged. Then he took out that mechanism and then he put in the gold plate. And then he observed the particles as they were going towards the gold plate. So, to kind of give you an idea of scale, imagine this is the alpha particle, this marble. Hank would be the gold nucleus. But Hank's going to be at the other end of the school. Okay? Here's the alpha particle. Hank, I'm going to take Hank and move him towards the other end of the school. And I'm going to be blindfolded, and I'm just going to randomly start throwing marbles towards Hank. what's going to happen most of the time? It's going to miss. What are the particles going to do? Go straight through, not be deflected at all. Now, every once in a while, and I'm going to use the tennis ball for this so I don't hurt myself or anything else. But let's say that if it hit just dead on, what would it do? It would bounce back. But, well, give that back. I missed. Throw that back. Well, okay. Now, but if it just hits off to the side, it's just going to get deflected. Okay? So, you're shooting these particles that you cannot see at a gold foil which appears solid. But what they found is the vast majority of those flashes of light were appearing directly behind the gold foil, like it wasn't even there. So that would be somewhat analogous to me taking this tennis ball and I'm going to throw it at that wall. Now, imagine I do that 1,000,000 times. And only 1 in 1,000,000 times would the tennis ball come bouncing back to me. Most of the time, the tennis ball appears on the other side of the wall. What would you conclude about the wall?
It's not solid.
No.
It's not solid. It's mostly empty space, right? 1 in 1,000,000, the tennis ball would bounce back towards me. So what they figured out is that out of this gold foil and these atoms, and this was so counterintuitive than what anybody expected, most of the time the particles went straight through. Sometimes they would get a little bit of deflection, literally 1 in 1,000,000, they would hit and they would bounce back. Now, these alpha particles that turned out later on, we'll see what you all remember from chemistry. Oh, that was sounding painful. So, what does the 2 plus indicate? Charge. The element is helium. The 4 represents the mass number. The 2 represents the atomic number, the number of protons, right? So it turns out that the alpha particles were actually a helium nucleus without the electrons. This is why they had a positive charge, because you had stripped off the electrons, okay? And once we get into nuclear physics, we'll study what we'll call alpha decay. There's alpha decay, beta decay, all this stuff. So Rutherford got extremely lucky. The particles that he was shooting out, didn't know what it was, were, compared to the mass of the gold nucleus, very small. So the gold nucleus basically acted as like an anchor. So that alpha particle, the helium nucleus, would come up, it would get close, and if it hit just spot on, dead center, because they're both positively charged, it would bounce back. Now, this was a huge problem in the scientific community. It's like, this is bad. And here's the reason why this is bad. It's like, how do you explain all of this positive charge existing in an infinitesimally small dot? So the analogy I'm going to give, I can give because I grew up with 3 older sisters. So imagine that you have 6 girls who hate each other, okay, who have nothing to do with each other. There was a Snapchat incident, a boyfriend incident, they wore the same dress to prom. I don't know.
How dare they?
Okay? They want nothing to do with each other. Like, if one sees the other one walking down the hall from the commons, they'll dive into the other hallway just to avoid walking down the hallway in them, okay? Want nothing to do with each other. However, if you take those same 6 girls and put them inside the Volkswagen Bug before it gets smashed into the wall, they are the best of friends. They're taking selfies, they're sharing stories on Snapchat, all of this good stuff. Oh, you're one of my faves, love ya. Right? Wonderful friends. But only if they are inside the Volkswagen Bug. If you get them outside the Volkswagen Bug, they hate each other again. So the same thing is true what they figured out with protons. Protons don't like each other. They hate each other because they're positively charged. So they had to come up with another force that was strong enough to overcome the repulsion of the electrostatic force. Now, this was not the most clever name that they ever came up with. So the new force they came up with was the strong nuclear force. Like I said, it's not the most clever name. It's the strongest force, and it acts in the nucleus, and it's a force. So they called it the strong nuclear force, not the most clever name. But what they do get bonus points for is that every force has to have like a charge carrier, something that allows the force to exist. The strong force is carried by a particle called the gluon. Okay? Not the most clever name for the force, but they have bonus points for, it's the gluon because it glues the nucleus together. Okay, that's kind of cool. Now, but here's the thing. It isn't like I have a proton over here, and all of a sudden, whoop, they're going to form a new nucleus. Go back to the days when you were in chemistry. What is the only thing that determines the type of atom that an element will belong to? One thing and one thing only. Number of protons. Change the number of protons, change the element. You can gain and lose chihuahuas. Chemistry is basically the study of chihuahua rearrangement. Okay? Water exists, H2O, because it has a stable arrangement of chihuahuas. Okay? Chemistry, you never mess with the nucleus. That's the rule, because it's not what they do, because the forces are too strong. You can rearrange chihuahuas. So everybody says, well, let's make gold. Cool, great, let's make gold. The problem is that you have to change the structure of a nucleus to make it into gold. That's incredibly tough to do. So the strong nuclear force is the strongest force. If I ever ask you, what is the strongest force? What are you going to choose? Strong nuclear force. Do not pick gravity. Gravity is actually the weakest force. So the strong nuclear force is stronger than the electromagnetic repulsive force. Because if it wasn't, what would happen? Yeah, you could never form a nucleus, and we would never be here having this discussion. Because you would never have a nucleus. Without a nucleus, you don't have the structure of an atom. So, but it acts over the shortest distance. So this is why everybody says, let's have fusion reactors, where you basically, the short version is you slam hydrogen and then you make helium. There's a slight loss of mass, and that gets converted into energy. Well, to get this strong force to work, you have to have these protons and neutrons to incredibly short distances. So it isn't like I could just put them side by side and they go, here to take over. Well, if that was the case, it would be very easy to make a new element. It's like, hey, you want some carbon? Go get some protons. We'll just like put them on the table and hit them and smash them together. And look, here, we made carbon. Cool. Okay? No. This is why, if you look at all the atoms that make you up, you go historically, all the complex atoms that make you up, the carbon, the nitrogen, the iron that carries your hemoglobin, all of that, because it's so difficult to change the structure of a nucleus, all the atoms that make you up were forged in the deaths of the first and second and third generations of stars. Statistically, the atoms that make up this hand came from a different star than the atoms that make up this hand. All of the DNA, the nitrogen, the oxygen, all of the structures of your DNA, all of the hemoglobin, all of that was created in the crucible of dying stars because it's so difficult to change the atomic number. Now, if you look at our universe, we have three main particles: protons, electrons, and neutrons. That only makes up about 5% of the universe, by the way. If you look at, quote, normal matter, that will only make up about 5%. It's called baryonic matter. Most of it is dark energy and dark matter. It's annoying and embarrassing because we know it's there, but we can't find it. It's like, what are you missing? About 78% of the universe. Really? Yeah, kind of weird. So the normal matter, we call baryonic matter, only makes up about 5%. And even then, we're missing about 2.5% of that. Again, awkward. But thankfully, when we made this model, you had protons, electrons, and neutrons. Everybody says, why do you need neutrons? Without neutrons, you can't build a stable nucleus. You can't even build helium without neutrons. Because the neutrons, you have two of them in helium, 2 protons and 2 neutrons. If you take away the neutrons, it's no longer stable. So the neutrons, the sheepdogs, balance things out. They basically go to the St. Bernards and go, fellas, can we just chill out? Can we not all get along? Okay, we have the strong force. We're all trying to live together in this really small area. Can we not all just get along? And that's the role of the neutrons, is to kind of balance everything out. So, there's the fourth force, called the weak nuclear force. Do not worry about it. If I ever gave you a multiple choice test, and I said, hey, what's the strongest force, or what's gravity? And if it's a multiple choice test, don't ever pick the weak nuclear force. It's not ever going to be an answer. I'm gonna tell you this right now. Is it important? Yes. If we don't have the weak nuclear force, we don't have fusion in the sun, hydrogen doesn't get fused into helium, that doesn't produce light, we don't exist because we don't have light from the sun. So, is the weak nuclear force important? Yes. Is it anything we're going to worry about? No. So, no gravity holds things together. The electromagnetic force, which we'll talk more about tomorrow, is the most diverse. You saw what happened back there with the electromagnetic force. And then the strong nuclear force holds the protons together. Okay, I'm done. I know the South people gotta go. And the homework, and then we'll start the first, the really big forces lab tomorrow. So, we're good.